So this is the objective of this lecture. And then we will see how, by having those entangled photon pairs, it is possible to do some nice application in imaging. So let us see the physical mechanism that we are using to generate the entangled photon pairs. So this physical mechanism, as I have already discussed, is spontaneous four-wave mixing. So in this process, what happens is that we have two photons that are propagating inside the optical waveguide, and then they do spontaneously annihilate by generated a pair of photons that are correlated in time and that do satisfy the energy conservation requirement by which the energy of the two pump photons add up and is equal to the energy of the two correlated photon pairs that are generated. And so in the four-wave mixing process, the energy conservation rules has to be satisfied, but at the same time also, as we discussed yesterday, the phase matching condition. And so if you do satisfy both the energy conservation rules and the phase matching condition, so then when you excite with a strong laser pump, you do generate a idler photon at lower wave number, at a lower wavelength, and a signal photon at larger wavelengths. Please notice the power difference, so this is in dBm, so it's a logarithmic scale, between the generated photon intensity and the pump intensity. You have to notice, you have to realize that the pump intensity was even filtered. So that means that the efficiency in the generation process is extremely low. So we do say that the efficiency is in the order of 50 or 60, minus 50, minus 60 dB. So extremely weak process. Even though the process is extremely weak, we do generate those correlated photons. One aspect that is very peculiar is the fact that in order to get the maximum efficiency in the generation, so we need to satisfy the phase matching condition. So let us go a little bit more in detail on the implication of the fact that we need to conserve the momentum in the process. So first of all, so the relationship between the momentum and the energy and the frequency of the photon is given by the usual relationship by which the momentum is equal to the frequency divided by the speed of light multiplied by the effective index of the mode. And you should remember that the effective index of the mode depends on the frequency as well. And therefore we have that K is equal to omega effective index divided by C. Now we plug this definition into the phase matching condition, and we end up with the fact that the phase matching condition that we want to have equal to 0 can be written as the frequency of the pump multiplied by the effective index of the pump multiplied by the effective index of the second photon and the energy of the pump minus the frequency of the signal photon multiplied by the effective index of the signal photon minus the frequency of the idler photon multiplied by the effective index of the idler photon. And here what we have emphasized is the fact that for each of the modes characteristic of the photons that we are considering, so we may end up to have a different effective index. And therefore, if we control the modes that are involved in the four-wave mixing process, we can control the phase matching condition. So let us assume to have that all the four photons are traveling in the same optical modes. So in this case, we have that, so now we can simplify by 1 over C. We could simplify by the effective index because all the photons are in the same mode, and so we end up that the phase matching condition is translated in a condition by which the energy conservation say that 2 times the frequency of the pump should be equal to the frequency of the signal plus the frequency of the idler. But since all the modes all the photons are on the very same modes, so this condition can only be satisfied when the frequency of the pump is almost equal to the frequency of the signal, which is almost equal to the frequency of the idler. As a result, if all the photons are all in the same mode, as a result we have that the frequency of all the generated photons are more or less equal. So if we do calculation of the efficiency as a function of the idler photon energy, so we end up with a spectrum that is similar to this one. So this is a simulation where we have considered that all the photons are traveling on the very same modal order. And so what you see here is that if this 1.55 is the wavelength of the pump, so you see that the probability, so the efficiency to generate photons that have a wavelength different from the one of the pump is going down exponentially very rapidly. So this kind of behavior is the manifestation of the fact that the generation efficiency is the sinc function of the phase matching condition. So as a result, so you have that all the photons are essentially, both the pump photons and the signal photon have essentially the same frequency. So the situation changes if we do go back and we try to use, instead of using the same optical mode, we try to use different optical modes. So in this case, what we have that for a fixed wavelength, so the effective index of the modes are different. So in this case, what happens is that now, so in this relationship, we cannot, when we put delta k equals 0, we cannot simplify the effective index. And therefore, it turns out that if we have different modes that are involved in the four-way mixing process, we have that the effective index is no longer the same, and so the energy conservation rules is satisfied when the frequency of the generated photons is not equal to the frequency of the pump photons. And this gives you a plot, a spectrum of the generation efficiency that is drastically different with respect to the one when we are using the very same optical mode. So this kind of process is called intramodal four-wave mixing, and is a process by which you see we have that the photons are traveling in different order modes. So this is one pump photon is traveling on the fundamental mode, this one is traveling on a first order mode, the signal is traveling on a first order mode, and the idler is traveling on the fundamental mode. And so therefore, so the process involves modes, so the first, the second, and the first mode. And as a result of the fact that now we can conserve the energy and satisfy the phase matching with different energies for the involved photons, as a result, what we have is that we have a large detuning between the pump and the idler on this side, and on the other side we will have the signal photons, a large detuning, so it's very easy to separate the pump photons from the idler and the signal photon, as well as, and this is going to be important when we will discuss about single photon sources, as well as we have a very narrow discrete band of high generation efficiency. So that means that by using different optical modes, meaning by using intramodal four-wave mixing, we are able to generate photon pairs that have an energy that is very far from the one of the pump, and they are generated in a very narrow spectral region. How do we control the detuning? So we do control the detuning by controlling the waveguide width. And so what happens is that the larger is the waveguide, the more, the less separated are the different modes, and therefore the generated photon wavelength, so the signal and the idler photon wavelength, are very near to the pump photon wavelengths. But then when we decrease the waveguide width, it happens that the modes are more separated in the spectrum, and therefore so we can generate the photon in the near infrared and the photon in the mid infrared. Okay? So by simply controlling the spectra, by simply controlling the width of the waveguide. And so this is a quite powerful tool in order to design the energy of the generated entangled photon pairs. So let us see how we can implement this process in an integrated photonic circuit. So here the issue is, how can we excite, how can we select the specific mode inside our waveguide? So this is the circuit that we have fabricated in order to excite generated entangled photon pairs. So this is a circuit that allows us to have an heralded single photon source of ultra-pure photons. And so, starting from the input, so here what we have, so we have a grating coupler. Now you should know what a grating coupler here is. So we have a grating coupler that through which we do insert the pump photons. And so this is the typical size of our waveguide in this example. So then here we have a 3D coupler, so a splitter. So this is based on a multimode interferometer. So we have, it's like a mirror, it's like a beam splitter here. So what happens is that here we have P0, and then 50% of the pump photons are going there, and 50% of the pump photons are going there. Then here we have the key component that we are using in order to be able to excite the specific mode inside the waveguide. This component is called an asymmetric directional coupler. A directional coupler is a device that allows you to couple together two waveguides, and if you control the spacing between the waveguide and the length of the directional coupler, now you can design your device in such a way that it enables to couple a fundamental mode from one waveguide. You see, this is the fundamental mode. From this waveguide is the fundamental mode that is traveling in this waveguide, and this fundamental mode is coupled with the first order mode in the second waveguide. Okay, so in this way, so what you achieve in this region here is a modal conversion between the first order mode to a second order mode, okay? Between the fundamental to the first mode here. And so this is the device that we are using, because now what happens is the fact that inside this waveguide that is large, because this is a multimodal waveguide, so this is thin, is a single mode waveguide. So what happens in this multimodal waveguide is the fact that we have that 50% of the optical power is traveling on the fundamental mode, and 50% of the optical power is now coupled through the ADC, through the asymmetric directional coupler to the first order mode. And so we are getting what we want to get in order to have the intermodal four-way mixing. And therefore, inside this waveguide that is large, we have the generation of idler and signal photon, meaning that we have the generation of our entangled photon pairs. And the energy of the photons that are generated is very far away from the energy of the pump photon. And so we have the idler photon at 1.29 micron and the signal photon at 2.03 micron. And now in this multimodal waveguide, which can be as long as you require, so you have that the idler photon is traveling on the second order mode and the signal photon is traveling on the first order mode. So then you use another directional coupler that now convert the second order mode into the first order mode. And so here at the output of the waveguide, what do we have is that we have the two entangled photons that are physically separated, and therefore you can do whatever you want with this pair of photons, and one of the two is in the mid-infrared and the other one is in the near-infrared. So the spacing between the two photons is controlled by the width of the waveguide. So decreasing the width of the waveguide, you increase the spacing. Increasing the width of the waveguide, you decrease the spacing. where are the pump photons? So the pump photons that you insert are still traveling here, but not traveling there because the pump photons are, so this asymmetric coupler is also isolating the pump photon from the generated photons. And therefore now here you have also the pump photon that you have to filter out. And so what happens is that now you have 3 output ports. So in one port you have the residual of the pump, then you can monitor if you want to do anything, control how much power we have, whatever, so you can control, you can monitor. This is physically separated from the idler photon that is in one port and the signal photon that is in another port. So this is a quite useful tool in order then to try to do, for example, an heralded photon source. So what we did, for example, in this further application is to use the infrared photon as an heralder and to use the signal photon as the heralded photon. And so what we do is that we generated an heralded single photon source. So let us see. Why do we need single photons then? So the question is, why do we need single photons? So what we want to do is that we want to pass from entangled photon state to a single photon state. So in this case, what we need to get is we need to get that instead of having correlated photons, we need to have uncorrelated photons in order that the state can be factorized in the product between the wave function of one photon and the wave function of the second photon here. How do we characterize the correlation properties of a two-photon state? So the quantity that we are using is called the joint spectral intensity. So in this case, we are describing the two-photon wave function, and this two-photon wave function is described as resulting from one photon that is in the signal mode, in the signal frequency mode, and one photon that is in the idler frequency mode. And so this is the probability to have the two photons, and this is the probability to have one photon at the signal, and here one photon at the idler energies. So then we have this quantity here that is the joint spectral amplitude that quantify the probability to generate the first photon in the state 1, 0, 1 omega s, and the second photon in the state 1 omega I. And therefore, if we want to say, if we want to have information about whether those states are factorizable or not, so what we have to do is that we have to look at the joint spectral intensity. And so the characteristic of the joint spectral intensity is to be a function that depends on the frequency of the signal photon and the frequency of the idler photon. And therefore, if we map the intensity of the joint spectral intensity in a two-dimensional plot, we have that here we have the frequency of the idler photon, and here we have the frequency of the signal photon. So the bandwidth in the phase matching condition, so the width frequency interval by which the omega s and omega I satisfy the phase matching condition, give you the extent, give you the width of the joint spectral intensity in this direction. The width of the pump laser give you the width of the joint spectral intensity in this direction. So now we have the joint spectral intensity, and now we can compare this joint spectral intensity of an extremely low purity single photon state with the joint spectral intensity on a very high purity single photon state in an heralding photon source. So what we have in entangled photon is the fact that the two photons are strongly correlated, which means that if we have a photon at this energy, we know that the other photon will have this energy. If we have the photon at this energy, we know that the other photon is at that other energy. So we have a strong correlation. Knowing the properties of one photon, we know the properties of the other photon. And the joint spectral intensity is essentially a line in this plot, while on the other hand, when the two photons are strongly uncorrelated, so we have that the joint spectral intensity has a shape of a dot, a square. So that means that knowing the energy of the signal photon, meaning if you draw a vertical line here, the energy of the idler photon is undetermined. Okay? So we have not a strong correlation between the two. In the if we consider this entangled photon state for a source of heralded photons, so what happens is that if you have a large degree of correlation, when you are measuring one of the two photons in the pair, so the resulting single photon state is in a mixed state of many different photons. Okay? So that means that we are measuring the signal photons and the idler photon is spread over a wide frequency range. On the other hand, if the degree of correlation is small, so we do not have anymore the oblique dependence, the correlated shape dependence between the frequency of the two entangled photons, we have a dot here, and so in a single photon source, what we end up is the fact that the energy of the single photon is very narrow in the frequency space, meaning that we have a very good pure state, a very good single photon state. And so this is what we want to achieve. So in order to achieve that, so we use our spontaneous four-wave mixing source. Let us see what we get in the case when we have intramodal four-way mixing, meaning that all the photons are all on the same optical mode. So the result is a joint spectral intensity of this shape. And so therefore we have a very correlated photon pairs. So the purity of the source that we are going to generate is extremely low. So people have solved this problem by using filters. Because now if we filter out, so we use a filter on the idler photon, a filter on the signal photon, so we remove all the other photons in this joint spectral intensity plot, we remove all those photons, and we end up with a joint spectral intensity that has the desired spot shape. And so the photon in this case is strongly uncorrelated, and we can use those photons as a single photon source. What is the problem here? The problem is the fact that we are filtering out a lot of photons, generated photons. And so the source will have a very low heralding efficiency, meaning we will have only few photons that are generated. And so we have to compromise the efficiency, so the brightness of the source, in order to get a high purity. The situation is different in the case we are using our intermodal four-way mixing. Because what you see in the intermodal four-way mixing is the fact that you have naturally that the generation bandwidth is extremely narrow. And therefore, in this case, you end up with a joint spectral intensity diagram where the generated photon pairs are distributed in a very narrow region that gives you a very strong purity in your signal without having the need to filter out anything out of the photons that you have generated. So in this case, what we get both a high heraldic efficiency as well as a very large purity. And so in this case, by using intramodal four-way mixing, you get very strongly correlated photon pairs. By using the intermodal spontaneous four-way mixing, we do get a very good separation between the two wave functions, meaning that in an heralding experiment, we can end up with a purity of the single photon state that is quite large. Still, the number, 76%, is not sufficient in order to use this single photon source for a quantum computing experiment. And therefore, we look at more carefully to the joint spectral intensity, and what we realize is the fact that you have some side lobes here, which are a consequence of the fact that the generation efficiency has a sink line shape. You see those side lobes there, so a sink line shape, which are compromising, which are reducing the value of your purity that you can achieve. And therefore, so we elaborated a technique in order to decrease even further those correlations, and so increase even further the purity. So this technique is based on the realization of the fact that in an experiment, what you have is that you are entering into your waveguide with two photons, which are the PAM photons, that start to interact as soon as the two photons enter into the waveguide. And so the overlap between the two photons inside the waveguide has a box-like function. So you enter here, from here, and then they do interact up to the end of your waveguide. And during this interaction, they are producing, by spontaneous four-way mixing, all the entangled photon pairs. So this means that this overlap, spatial overlap of the PAM photons transfer into the sinc function shape of the generation spectrum. And in order to move from here to there, so the operation that you have to do is a very simple Fourier transform. And so if we want to remove this side lobe here, what we need to have is that we need to change the shape of this overlap between the two modes. And so in order to do that, by using the intramodal four-way mixing, we do realize that indeed the two photons are traveling in two different modes. One is characterized by a large group velocity, so the fundamental mode has a large group velocity, while the other one is characterized by a lower group velocity. And therefore, what happens is the fact that they do travel through the waveguide with a different speed. And now what we can do is that if we do delay one of the two photons in the pair, in the pump pair, so we can design the situation in such a way that we get a maximum overlap inside the waveguide. And therefore, so what we do is that we can use this technique. We slow down the fundamental pump photon in such a way that the spatial overlap between the two photons is slowly increasing within the waveguide due to the fact that this photon here has a lower speed, and so it takes more time to reach the center of the waveguide. And so we end up with a situation where we have a small overlap between a progressive increasing of the overlap between the two photons inside the waveguide. They do reach a maximum overlap in the center of the waveguide, and then the overlap decreases because the fundamental photons overcome as a larger speed than the photon that is traveling on the second order mode. And so now, by using this delayed approach, so we can get a variation in the overlap of the two wave function, the two photons inside the waveguide, that is moving from a box function to a Gaussian overlap function. And now the Fourier transform of the Gaussian is still a Gaussian. That means that we have completely removed the side lobes. And so this adiabatic turn-on of the spontaneous four-way mixing enable us to get a joint spectral intensity that has a number that is similar, that is approaching the perfection. So you see here that the purity is 99.04%. We have an extremely low correlation. How can we get that? By introducing in the schematic, in the circuit that I've shown you before, a serpentine by which the photon mode that is traveling on the fundamental order is slowed down with respect to the mode that is traveling on the first order mode. And therefore, the overlap within the multimodal waveguide is increasing slowly, reach a maximum, and then it decreases. As a consequence, the two photons that are generated, the correlated photon pair, the entangled photon pair show an extremely low correlation, and we end up with a very low purity by not compromising the heralding efficiency. So we get a very large heralding efficiency and an extremely large purity. So we do wonder, are those photons really pure photons? So we perform a quantum interference between the two photons, and we end up with a quite large number of indistinguishability. So if we have two photons, two sources that generated those heralded single photons, we do perform an interference experiment, and we do end up with a very large heralding efficiency. Even more, if you do an experiment, which I have already told you, the Ongo-Mandel experiment, you have that the zero in the Ongo-Mandel is approaching, the zero is a real zero, which gives you an indistinguishability of 99.6%. And everything here is done by using two sources that are integrated in the same circuit. Okay? Here you see the input. You have that the pump laser is input here, is split in two sides. So one is used to pump source 1, the second is used to pump source 2, and the source 1 and the source 2 implement the time delay approach. You see here the serpentine of one source, the serpentine of the other source, and then what you do, you take your single photon, so one you use as an heralder, the other one instead you use in order to do experiment. So these are the joint spectral intensity of the photons coming out from one source. These are the joint spectral intensity of the photon coming out of the other source. If you do overlap the two, you get an indistinguishability that is in the order of 99%. So extremely high. Okay? So in this way, so by using this approach, so we can remove the correlation between the photons, and therefore, so we can get sources of extremely high purity. We can even integrate two sources in a circuit, so we get a very large degree of indistinguishability. We can also integrate more sources, and therefore now we have as many photons, single photons, extremely indistinguishable as we wish. Okay? In this approach, so we can go up to 50 single photons, extremely indistinguishable on the same circuit. And in this way, so you can enable quantum technologies. So we got a patent on this approach, and we try to sell the patent to PsiQuantum, that company that is making quantum computing by using silicon photonics. Here I do want to show you a couple of applications of these single photon sources. So the first application would be in the mid-infrared. So how can we measure mid-infrared photons? And the reason why we want to measure mid-infrared photon is for doing sensing. So you know that the different molecules have different absorption in the mid-infrared, so they are very characteristic by their absorption. And so you have a sensor of the presence of carbon dioxide in the ambient. And therefore, what we need to have is that in order, if we want to sense carbon dioxide, so we need to have a photons that has this very specific energy. If we want to measure, for example, oxygen nitride, so we have to change the wavelength. If we want to measure sulfur oxide, so we have to change the wavelength. Methane, so we have to change the wavelength. So each single wavelength is able to probe a single very specific gas. And so this is an approach that is used in order to make a gas sensor quite easily. So here we have a problem that if we want to sense a gas in an ambient where you have a high environmental noise, so at the end you are not able anymore to measure anything because the noise is overcoming the signal that you are trying to measure. So the signal is nothing else than the transmission of your photons through a chamber or through the ambient where you have your gas. And so what we tried to do was to implement in a very small photonic integrated circuit a gas sensor that is able to work even in the presence of a high environmental noise. So the first thing that we did was to design our system in such a way that is able to generate a photon in the region where exactly carbon dioxide is able to absorb. Okay? And therefore, so we do use spontaneous four-way mixing in order to generate those photons. And here is the circuit that is characterized by a waveguide with a very well specific width, by which we have that the signal, the idler photon is generated at 1.3 micron roughly, while the signal photon is generated exactly where carbon dioxide is absorbing. So the problem here is that if we want to measure the transmission, so we have also to measure this photon here at 2 micron. So measuring at 2 micron has the problem that at 2 micron you have a strong signal coming from the black body radiation. So here is the spectrum of a black body, and what you see in the black body is the fact that you get a quite large signal in the infrared. So if you want to develop a sensor, a photodetector in this spectral region, so you have to beat the high thermal noise that is present typically in this region. So one way to do that is to cool down the sensor so that you reduce the temperature. So by reducing the temperature, you shift the black body radiation to longer wavelength, and so you remove the thermal noise. But doing that, so there is a problem, because if you want to cool down the system, so you need to have a cryostat. And the cryostat is expensive, so it costs you money. And therefore, so we have developed a technique that is based on nonlinear optics in order to avoid to use low temperature detector, and even in order to use a silicon detector. And the idea is to use a second order process that is called some frequency generation. Okay? I have already told you about nonlinear effect. So in this process, what you do is that you simply mix your 2 micron photon with a pump photon in order to translate the 2 micron photon into a visible photon. And you have to design your circuit in such a way that the sum of the two is equal to the frequency that you want to detect. And then once you do that, so you can make a detector that is able to move the photon from 2 micron to visible light. And so this is the detector that we have fabricated. So here you have the pump laser. So the laser is pumping the nonlinear crystal, and in the nonlinear crystal you have the zoom frequency generation effect with the conversion efficiencies of 20%. Okay? The result is quite appealing, since people have, we have published this in Nature Communication in collaboration with a Dutch research group that now has, has been patented, and now this Dutch group is selling this kind of detector. So then, now we do use our source in order to be able to herald the single photons. And in order to do that, so we characterize the characteristic of the source. And so, and then we compare our source with other sources that have been published in the literature. And so what we obtained was a characteristic that, a source that had very good characteristics in terms both on the probability of generation. So you see, this is measured per square watt, Y square, because you have 2 photons in the pump. and you see that we get a generation probability in the mid-infrared that is larger than other kind of approaches. And then we get a source with a low noise. So this number here is the coincidence to accidental ratio, and this is quite important number to characterize a single photon sources. Coincidence means that you have that the signal and the heralded photons give you a coincidence signal, so they do arrive at the same time on the two detectors. And then the noise is when the detector clicks, either one or the other detector clicks. And so in this case, you have a situation where the photons, the clicks, do not represent a good count, a good coincidence. And therefore, what you do is that you quantify the noise in your source by measuring the ratio between the good coincidence, that are those that happens at delta t equals 0, with the what you call the accidental coincidence, that are those that are caused by the noise. Okay? The larger is the larger is this number, the better is the situation, because for large car you have a large number of good coincidence with respect to the accidental coincidence. And so this is a number that people is using in order to quantify the quality of the source that they are producing. But let us see the kind of approach that we are using in order to improve the signal with respect to the noise in our mid-infrared transmission experiment. So the technique is a technique that is called a ghost spectroscopy. This technique is a quite funny technique by which you are doing the spectroscopy on a photon that didn't interact with the gas that you are looking at. And so in this technique, what you do is that you are measuring, you are doing a spectral measurements on a photon in an entangled photon pair, while the other photon in the pair is interacting with the gas. The only requirement is the fact that you need to have a detector that is able to count when a mid-infrared photon has been transmitted by your gas. So you use this signal of detector, of the bucket detector, in order to trigger the measurements of the other photon in the pair. So in this way, essentially what you do is that you need to have a standard, a low-cost bucket detector in this side of the spectrum, while you need to have very high-quality system which are able to do a spectroscopy measurement, so a dispersive element, as well as count very accurately on the other side, on this other side of the spectrum. What is the advantages in our case? In our case, the advantage is that at 1.2 micron, we have quite available system, quite available detector, low-cost system, because this is the region where telecom is working. While in the mid-infrared, so everything is very expensive. And so by using this ghost spectroscopy technique, you have several advantages. The first one is that you are doing a time filtering of the noise. Why a time filtering? Because you are measuring here only when a photon is passed. And so all the noise photons are not taken into account, because only those good photons are considered. The good photons are the ones that are resulting from the correlated photon pairs. Then, the second important aspect is that you have a ghost information translation. And this is the reason why it's called ghost spectroscopy. Due to the entanglement, you have that the energy of the photon in this side of the pair, of this pair, is exactly entangled, meaning that you know exactly what is the energy on this other side of the pair. And therefore, it happens that when a photon of a given energy is transmitted, you know that the counterpart photon is also transmitted in this other side. So that means that now, if you do the spectroscopy of the photon in this side, you know the energy of the photon that has moved and has been transmitted by this other side. And so what you do is that by using the entanglement, you are translating the spectral information from the near infrared to the mid-infrared. And so by doing a spectroscopy on the near infrared photon is the same as doing the spectroscopy in the mid-infrared photon. And therefore, in this way, you avoid to do the spectroscopy in the mid-infrared photons, and you do only the spectroscopy in the near-infrared photon, where you have low-cost systems. And finally, by using intermodal spontaneous four-wave mixing, you can get a larger spectral shift between the twin photons, between the entangled photons, meaning that now you have the possibility to have photons in the mid-infrared where they should be absorbed by the gas. So let us see the kind of experiment that we are performed. So the first experiment was a simple absorption experiment, and the second experiment was a ghost experiment. So the simple absorption experiment is an experiment by which you have that your mid-infrared photon is going through the gas, and then through a high environment noise region, and then it is detected. So here you have detection in the presence of a large noise. On the other side, in the ghost spectroscopy measurements, we have that this arm here is exactly the same. However, what we are doing is that we are measuring the idler photon, meaning that the photon that is not affected by the noise. And by using the ghost approach, so we can get a time filtering as well as a spectral information translation onto the photon that we are measuring. So let us see the result. So this is a result of a spectrum. Okay, so this is a transmission versus the wavelength. And what you get is that in the standard absorption measurements, you see a very weak signal, while in the ghost measurements, you see a very large signal. And so this is a big advantages. So you end up having a very large improvement in the sensitivity of your measurement caused by the technique that you are using. Look here, what you have is the change in the transmission when you are changing the pressure inside the gas chamber. In the case of a standard, a classical measurement, you see that by changing a lot the pressure in the gas chamber, you get a very weak change in the transmission, meaning that the sensitivity is extremely low. You are not able to distinguish a great change in the pressure because of the noise, while in the other case, you are getting a large sensitivity improvement, meaning that now you are sensitive to small changes in the pressure, and those small changes in the pressure gives you a large change in the transmission. And so by using this technique, you have completely solved the problem of the noise. As far as the spectral ghost information, spectral information translation, so this is what you get, the resolution that you can get. You see that you are able to resolve all the vibrational line of the CO2 moleculars by using a filtering, by using a spectral analysis of the idler photons. And so this is indeed what we want to achieve. So in improvement in a ghost spectroscopy, in improvement in a mid-infrared measurements by using the technique of entangled photon generation. But yesterday I showed you this movie, okay? And I say that I will show you and I will explain you why we can do undetected photon spectroscopy, okay? Now, we take the very same system and we remove this detector, okay? So the idea here is to try to do a measurement without looking at even by using a bucket detector at the other detector in the pair, okay? So what we do now is that here we are still looking at the mid-infrared photon. Now we remove completely this mid-infrared photon. And so the technique is indeed called the ghost is called the undetected photon spectroscopy technique. And this technique, you see what we are doing. So we are inserting a piece of paper in the idler in one photon of the pair, maybe it's the idler, I don't remember, and then we are simply looking at what happens as an interference in the signal photon. And you see that we are able to see the object that is moving there, as well as the piece of paper that is moving in the photon that we are not looking at. So the technique is based on this paper, that is a paper published by the Nobel Prize winner Anton Zillinger, and this is the reason why he got the Nobel Prize. And essentially, the technique is based on the use of indistinguishable photon. So here, the idea is the fact that if you cannot distinguish the photons, so then you can do an undetected photon measurements, because now, if you cannot distinguish the photons, so you can get quantum interference between the photons of the generated pair. So let us try to understand exactly what we are doing. So in the undetected photon spectroscopy, so we get a photon, so we met one of the photon interact with the object, and then we look at the other object. So not at the object that we are, not at the photon that is interacting with our object. Okay? And so now the goal is to try to understand why this is possible. How can we indeed achieve this? So we start from the scratch. And so the first thing that we have to understand is the quantum Mach-Zehnder interferometer. Okay? So let us consider a Mach-Zehnder interferometer. So a Mach-Zehnder interferometer is an interferometer where you have two paths, and then you have that you change the phase of the light that is traveling in one of the two paths, and then at the output, what you end up is that with an interference diagram. And the interference diagram is measured as a function of the phase shift between the photons that are traveling between the two paths. So this you know, okay? So this is simple. Now we use this interferometer by using a single photon. And so if we have a single photon, now we do consider the fact that the photon at this beam splitter here is transmitted by this beam splitter in a superposition of states. In a superposition of the state of one photon that is traveling this part here, and the same photon that is traveling in this second part here. And therefore, we don't know, after this beam splitter, where the photon is. Okay? And so if we want to describe the single photon state, we have to describe the single photon state as the superposition of a photon in this path here and a photon in that path there. Okay, so this is clear. Then we do have that the photon that is traveling in this path here arrive in the region where we add a phase shift. And therefore, now the photon in this path here is described by the wave function characteristic of the photon that has moved in this path, plus a term that represents the fact that the photon in this path has been phase shifted by a certain quantity gamma. And so now the wave function of the photon results from the superposition of the photon that moved there and the photon that moved there. But we still have one single photon, not two photons. So this is a superposition between the probability of having the photon in this path here plus the probability of having the photon in that path there. At the end, here, what do we have? We place a counter, and then the counter is measuring the probability that the photon moved there or the probability that the photon moved there. And therefore, as a result, so what we have the quantum interference between this path, the photon that moves in this path, and the photon that moves in that path. As a result, we have a quantum interference, so an interference that depends on the phase shift between the path A and the path B. Okay? But we still have a single photon, not two photons, one single photon. Now we can redo the same experiment. Instead of considering which path, so the two paths, we can use two sources. So now if we have two sources of indistinguishable photon, so we have that the wave function of the photon is equal to the probability of having the photon generated by this source plus the probability of having the photon generated by that other source. We still have one photon, so we are always dealing with a single photon. But now we have that the photon can be generated by this source or the photon can be generated by this other source. But the description of the physics is exactly the same. So it's not different. The only difference is the fact that instead of considering the path here, we are considering the source. It can be generated by this or can be generated by that. The result of the measurements at the end is the very same quantum interference diagram. Okay? Now what we do is that we take the two sources and we do superpose. We do make one source after the other. And therefore here in this experiment what we have a first source here, a second source there. We don't know from which source the photon is generated. It can be generated by this source or can be generated by this other source. What we do is that we place a phase shifter in between the two sources. And so therefore, at the end of this path, what we have is that we have that the wave function is given by the superposition between the photon generated by this source or the photon generated by that source, modulated by the phase shift that the photon generated by this source has taken. And therefore, we have a quantum interference spectrum here. Now we take a source that is able to generate entangled photon. And so we have the first source that is generating two photons. Then we put the second source. And in the second source as well, we have the probability to have the generation of an entangled photon pairs. And now at the end here, we have that the wave function results simply by the superposition between the photons, the idler photon that is generated by the first source, plus the signal photons that are generated by the second source. But we don't know whether the photon has been generated by the photon pairs has been generated by the first source or whether the photon pair has been generated by the second source. And now what we do, we add an object, so a phase shift, in the line that is traversed by one photon generated by the first source. And therefore, since we are adding this phase shift, so we have to add this term when we are computing the probability because the photon, the red photon here, has suffered this phase shift. But now what we do? Instead of measuring this photon here, we are measuring the other photons. But we are doing these measurements by using entangled photon pairs, meaning that those photons are entangled. So that means that the phase shift that is suffered by the photon that is moving along this path is transferred in the measurements in a quantum interference effect on the photon that is traveling on this other path. And therefore, what we get is that by measuring the blue photons only, we are able to measure this phase shift, which means that we are able to measure what the red photons has observed. Is it clear? Any question here? This phase shifter? Yeah. So this is the object that Chiara was moving in the beam that I've shown you. Okay? And so what happens is that so the presence of this object here is transferred in the observation of the presence of this object in the blue photon there. Okay? And this is possible only because the two photons are entangled. Okay, so it's the entanglement that allows us to transfer the information from the red to the blue photon. But what we need to have here, we need to have, since we are doing a quantum interference experiment, we need to have two photon sources that are able to generate single photon pairs, exactly indistinguishable. So we need not to be able, by looking simple at the photons, to know whether the photon has been generated by this source B here, or whether the photon has been generated by this source A there. Okay? So the key ingredient here is the fact that we don't know whether the photon came from this source or whether the photons came from that other source. In this case, we have a quantum interference between the probability of the photon generated by this source and the probability of the photon being generated by the other source. Is this interference that is measured in the quantum imaging experiment as a disappearance of the interference here or not? Okay? So is this interference the key ingredient? Both sources can give, but we are in a region by which, in a single time interval, only one source is generated a pair. Okay? So here the key ingredient is the fact that we need not to know whether the source A or the source B has generated a photon. Okay? So we are in a single photon regime. Okay? Very weak signal. And so this is the experiment. So we do integrated experiment in a chip. So this is one of our chips. So this is 1 millimeter length. You see that we have many circuits, but what we are interested is this specific circuit there, where we have the input fiber, where we have the PAM photon, and the output fiber where we measure only one of the two photons generated in the pair. Then we do a quantum interference experiment in the chip. So we generated our photon pairs. We do separated photon pairs. So then we do introduce a phase shift in one of the two photons of the pair. Then we recombine the two photons. We move the two photons in the second photon source. And then at the end, so we measure not the photon that was phase shifted, but we measure the photon that has not interacted with the phase shifter. And so here you see the fact that we have an interference diagram on the near-infrared photon by changing the phase of the mid-infrared photon. And so this is quite good. Or on the other side, so we can do the experiment that I've shown you. And this is not an integrated experiment, so this is a tablet-top experiment. And here the idea is to use a single nonlinear crystal where this spontaneous parametric process occurs, that is traverses 2 times by the PAM photons. And therefore we have that in reflection, so we have that this single nonlinear crystal behaves as two sources. Two sources because we have the first PAM photon, so the green line, that is going through the first time. And so this is the first source. Then it reaches a mirror and is going back a second time, and this is the second source. So we have a reflection experiment. But in this way, so we have that the PAM photon is traversing the nonlinear crystal 2 times. And so it's exactly the same. So the actual experiment is the fact that we have one crystal. The PAM photon is going in one direction. Then here we have a mirror, and the PAM photon is going back. And so in this first path, we have the first source. In the second path, we have the second source. And then what we do? And then in the first path, we have the generation of the idler photon. And then we have in the first path, we have the generation of the signal photon. The idler photon generated by the first source is reflected back, is going through. And here we have the idler photon generated by the first source plus the idler photon generated by the second source. And so we have the two sources photons there. And then what happens here, we have another mirror. And so the signal photon is going back, is passing through. And therefore here we have the signal photon generated by the first source plus the signal photon generated by the second source. But what we do is that we look only with the detector, with the camera, the photons that are the idler photon, not the signal photon. And then what we do in the experiment, we put an object here. By placing the object there, we are able to observe the presence of the object in this place here. Okay? So this is the idea of the experiment. And this is indeed what you have here. Okay? So you enter, the pump photon is being reflected here, it's passed again there, and then it's gone. And in the first passage, we have the idler photons that are generated, the yellow one, so they are reflected, they're going down. And then here we have the idler photon generated by the second passage of the pump, so we have the second idler photon, and then we get the camera. And then on the camera, we observe the interference between the two photons generated, between the probability of the photon being generated by the first source or being generated by the second source. And then here in the red, we have what happens to the signal photon. So the first signal, the first passage of the pump generated the signal photon that is going down. Then the second passage of the pump generated the second signal photon. And this signal photon is blocked there. And so here we have the quantum interference caused only by the idler photon. So we are not looking at the signal photon. And then we put an obstacle here. For example, this obstacle is a flower. But this obstacle is placed in the path which is traversed by the photons that we are not looking at. And by looking at the photons that do not interact with the obstacle, so you see that we are able to observe a quite good images that reproduce the obstacle that we were looking at. Even we can go to high resolution, and we go to very high resolution, and this means that we can do a quite good imaging by using this approach. Any question? Now, do you understand this experiment? Is it clear now how it works? You believe in this experiment? So you believe that this is indeed an experiment that proves that the quantum mechanics is working? That Einstein was wrong? Quantum mechanics entanglement phenomena is not a Spocky action. So he was saying that entanglement is a Spocky action, meaning that should be something else in the theory that in the nature that we are not able to describe. And so you see that, no?
By observing these many experiments, we can make us believe like yeah. But still, Einstein, whatever he gives the question mark, it still like seriously, quantum entanglement is hard to believe from.
Yeah, looks magic, huh? Yes. Look magic that you are indeed. So you are looking at the other photon. So this photon here that is producing this image never interact with the object, but simply because they are quantum correlated, so we are able to transfer the information from one photon to the other photon. And this information translation is non-local. You see the two photons are physically separated. So the translation of the information is non-local, as well as is fast, okay? So as we block, we immediately see the change in the intensity. Okay. So by said that, so here I have listed a few references that in case you are interested, so where we are describing what I have tell you today. And now I think that we can take a break for a coffee break, and in the next hour, in the next lecture, I will talk about quantum random number generator. So the application of quantum in cryptography. Yes? QKD, I have no time to go into QKD. Any question? Okay, so then I think that, yes. Yes.
So you have made a weighted width of somewhere around 500 nanometers. What is the weighted width?
In this multimodal waveguide, 2 micron.
2 micron. Okay. And you also have a sidewall, right? So does the roughness of the sidewall affect the experimental results in some way?
So this is also another advantage of the multimodal of the intermodal approach. So it's the fact that the sidewalls, since you are using different modes, so the sidewalls are not so dramatically affecting what we are observing. However, in this,
They are all multi-mode.
yes. So in this experiment, so the one where we are able, so here you find all the details, but the one where we are able to get this single mode, these very high numbers here. So the waveguide, so this waveguide here is a multimodal waveguide, because, so this is a single mode. This waveguide here is a multimodal waveguide. But the chip were fabricated with a very high quality processing, by which the propagation losses, I don't remember exactly the number, but should be in the order of 2 dB per centimeter, extremely low. But the losses here are really an issue, because since we are working with such a low efficiency, record efficiency in terms of single photon generation, but practically is a very low efficient generation process. So any photon that you lose means that your measurements time gets longer. So just to give you numbers, so this in this experiment, which is a fourfold correlation experiment. Why 4? Because we have 2 sources, so we have 4 photons generated. One of the photons generated by the first source should be used in order to herald the presence of the other photon. So one photon generated by the first source should be used to herald the generation of the other photon. And then we need to measure the coincidence event, which are triggered by the measure at the same time of this photon and of that photon. We need to measure coincidence event between those other photons. So at the end, we need to have 4 detectors that click at the same time. And so that means that we have a very few number of events here. You see, 140 events. So that means that we need to stay there to do measurements for a day. Okay? So this is a day-long measurements in order to do this simple plot here. So that gives you an idea of the fact that every single photon counts here. So we cannot afford to lose any photons, because any photon that you lose, it means that you take more time to acquire data. Now I should say that the numbers have been improved. So So this work here was in 2020, I guess. I don't remember exactly. Yeah, so it was published in 2020. It means that experiments have been done in 2019. Okay. This is a result from a collaboration between our group in Trento and Bristol University in England. Other question? So if not, we can have a tea time. Okay, thank you.
Duplicate mode.
Okay, so if you can correct, should be extended.
Yeah, in extended mode only when you show some presentation it will be visible.
Okay.
Else it will be look like this.
Okay. Okay. But now it's in extended mode.
Yes.
Okay.
So when you present something it will show.
Okay, good. Yeah, please.
you yesterday. Very yesterday. And I also know you were absent. You don't have to tell me like yeah. No, why? ठीक है पक्का 2 बजे वही डिस्प्ले करते
आप लोग चाय नहीं ले रहे हैं क्या? दे दूं उनको? आप लोग
Yes. Okay, so let me start the last lecture of the day and actually also of the course. And this is on quantum random number generators. And so first I would like to start, what's happening here? Oh, I'm pressing the wrong button. So first I would like to start with some motivation why we do want to do that. So here is, so there is a website where